Hi folks, so in this video we're going to start our reintroduction to quadratic functions, and we're just going to talk about kind of what we already know. So if we remember from Algebra 1, a quadratic function is something that looks like this. So a quadratic function, and we are going to talk about functions specifically now. We will see examples of quadratic non-functions later. So a quadratic function is something of this form. Will look like this. So I'm going to use, because it's a function, it makes sense to use function notation. I'll use function notation. So f of x is equal to ax squared plus bx plus c. So this would be in standard form. We're going to talk later how there are other forms. So this is standard form. And of course, a cannot be 0. Let's not forget that part. The reason being, if a was 0, well, if a was 0, then f of x is just simply bx plus c, and this would actually be linear. Right, so that's why it's necessary to point out that a cannot be 0. But this is what we know and love, and we kind of remember what this graph would look like. So I'm going to draw an example, and we'll just see its graph. Alrighty, so here's the equation, or the example that I've drawn up. It's f of x is x squared minus 6x plus 2. And so we can see, if we remember, the graph that this makes is a parabola. That's the name of the shape that we assign to it. And therefore, it has this thing down at the bottom. So that bottom piece, and sometimes you have an upside down parabola, so that would be at the top if that was the case. But this bottom thing, we just call that the vertex. And in this scenario, we actually have two x-intercepts, which we can see there. Now, it's totally possible. If we raise the parabola, assuming it's upward, if we raise the parabola, eventually we will have only one x-intercept if the graph looks something like this, in purple, like that. Or it could have none if you raise it far enough up, like that. So it's definitely possible to have 0, 1, or 2 x-intercepts. But the fact that this is a function still, we can see that there is only one y-intercept. And hey, lo and behold, that y-intercept is at 2, which happens to be in our equation right there. That should make sense because we can easily see that if I just throw in 2 for x, so f of 2, well, that'd be 0 squared minus 6 times 0, plus 2, which is 2. And so wherever you see, if you have a function, f of 0 is always going to give you your y-intercept. Now, it's a little bit trickier to get your x-intercept because then you would have to figure out, well, when does f of x actually equal 0? And that would end up being something like this. Now, we'll talk in the next video about how to actually solve this. There are several ways, as you might remember. But the other thing I want to point out here, whenever I'm asking you to graph something, you might be asked about something called the symmetric point. Now, what's nice about a parabola, well, nice is relative, is that there's always this line of symmetry that goes through the vertex, remember? And so what that just means is that, hey, if I take this dashed line here, oops, and I always draw a dash so you don't confuse it for actually part of the graph, is that if you take that line of symmetry and you kind of fold your paper over it, then your parabola is going to land on top of it. So this purple side, if you fold this entire parabola over that dashed line, that purple side is going to end up on top of the red side. Okay, so this red dashed line, that is our line of symmetry, although you might see in some places called the axis of symmetry. What we're going to do to find the symmetric point then is you just need to figure out the point that is symmetric to what we'll say is the y-intercept. And so, hey, if I highlight it, here's our y-intercept right here in yellow. The question is, what point on the parabola is symmetric to that? Well, remember that because it's symmetric, then the distance from this point right here to the line of symmetry, or the axis of symmetry, whatever that is, call it d, is equal to this distance right here, where this would be the symmetric point in green. So that's also d. Now we can see where that is because that distance from the y-intercept to that line of symmetry is just where the vertex is. Because notice, that the line of symmetry always goes through the vertex right here. And therefore, if the x-coordinate of the vertex is 3, then that distance there is 3. And likewise, to get to that symmetric point, you have to go 3 again. So total, you're going 6, and so the x-coordinate of this point right here would be 6. Now remember that it's symmetric, and so if it went up some distance, if the y-intercept went up some distance, then that symmetric point went up the same distance. And so if this y-intercept is at 0, 2, then the y-coordinate of the symmetric point would also be 2. So this is what we'll call our symmetric point. So when you're graphing, we need for sure the vertex, the x and y intercepts, and that symmetric point. Alrighty, so in the next video we'll talk about how to actually get the x-intercepts, because that's always the hardest part.